starting shortly. Good afternoon, everyone, and thanks for coming to ESO and for joining us online. We have some unique observations to tell you about today. I'm Richard Hook. I'm Public Information Officer at ESO, and we're at ESO's headquarters in Germany. The format of the press conference will be as follows. First, we'll hear from ESO's Director General, Xavier Barcons, who will make a few opening remarks. We'll then hear from several of the lead scientists involved with this new result. Professor Reinhard Genzel, Director at Max Planck Institute for Extraterrestrial Physics, very close to here. Dr. Frank Eisenhower, who's a senior astronomer, also at MPE. Françoise Delplanque, who is Head of Systems Engineering here at ESO. Karine Perrault from IPAG, Grenoble in France. And finally, Odell Straub, who is at the Paris Observatory. We're also pleased to welcome other experts involved with this work, including Stefan Gillessen and Oliver Poole from MPE, and also Wolfgang Brandner from the Max Planck Institute for Astronomy in Heidelberg. After all the presentations, journalists will have an opportunity to ask questions, first here at ESO, and then those submitted by email. People online who wish to submit questions should email them to media@eso.org. There is also a hashtag for Twitter, which is on the screen. So, to start things off, I'd like to ask ESO's Director General, Xavier Barcons, to open proceedings.
Thank you very much. Welcome to ESO, to the European Southern Observatory headquarters in Munich, in Garching. As you all know, we are an intergovernmental organization. For the last 55 years, we have been building and operating very powerful ground-based observatories, very powerful telescopes, thanks to the support from the currently 15 member states that form ESO. We're very proud of our mission. We build these big machines and then we foster cooperation with the scientists in the member states, including our very near neighbors here in the Garching campus. Today we're gathering here to learn about a really transformational scientific result that has been achieved thanks to the very close cooperation and a lot of effort that we have deployed together with the colleagues in the institutes. As I said, we run a number of observatories in Chile, in northern Chile. The jewel of the crown is the Paranal Observatory, which you can see in this image. It contains the VLT, the Very Large Telescope, 4 8-meter telescopes, and the VLTI, the interferometer, which is essential for this piece of work, which can use either those 4 telescopes or the other 4 smaller telescopes that can move along this platform. Paranal is really the cathedral of ground-based optical and infrared astronomy these days, and I'm very proud that it has been the tool that has been so helpful to reach the scientific result that we're going to hear in a few minutes. Of course, none of this comes for free, as I said. Back in 2007, ESO took the decision to embark in a very challenging adventure to deploy an instrument which is called Gravity. You will hear about it in a few minutes. And in the last years, actually since early 2015, ESO decided to make the observations that you are going to hear about today the absolute priority for the organization. In the meantime, we supported lots of developments, including detector development, fit out of some of the telescopes, reducing vibrations, etc. You will hear all about it during this talk. But the most important outcome that you have to take away today is the greatness of the science result that will be explained to all of us. For me, I was trained as a theoretical physicist. This is a very special day. We're making a very big step forward in understanding and making sure that general relativity is correctly the theory of gravitation. So, welcome everyone, and let's enjoy the day. Thank you very much.
Thank you very much, Javier. Now please welcome Professor Reinhard Genzel, Director at Max Planck Institute for Extraterrestrial Physics, who will begin today's presentations.
Thank you very much. Well, it was a little bit over 100 years ago that Albert Einstein reformulated the theory of gravity, taking into account the finite speed of light and the fact that masses can be thought of as distorting the space-time in which then other masses orbit, move. And that theory has, clearly been at the helm of deep thinking in physics, and has predicted some things which are rather strange, one of which are black holes. These are objects which are so concentrated that nothing, not even light, can escape from their surface, if you like, their event horizon, and which attract, of course, other objects. Now, that was 100 years ago. About 50 years ago, the first astrophysical work started in studying such objects. X-ray astronomers found very compact binary sources, which we now know are stellar black holes of a mass of typically 10 solar masses orbiting each other and other stars. And the discovery of quasars by radio astronomers and optical astronomers showed us another class of objects which are likely black holes, but very much more massive, between a few million to a few billion solar masses, and typically located in the centers of Milky Ways. Now, these are all at first speculations. The question is whether indeed objects like massive black holes exist, and whether, if we could come close to them, they do look like the theory which Albert Einstein started. So that's the path. Now, unfortunately, quasars are very far away, and it's, even with modern technology, not possible to go right into the very central region around these black holes, which are influencing their environment, and where the event horizon has the scale of the sun or the solar system. So we have to, if you want to study these objects with detailed methods, we have to come closer. And the ideal object, in fact, has turned out to be the center of our own Milky Way. It's not a quasar, but it's 26,000 light years away, by a factor of 10,000 closer than the nearest black holes. And so a group of us, and a little later a group in California headed by Andrea Ghez, started in the 1990s, we with telescopes of ESO and Andrea with the Keck telescopes, to study the central region of our Milky Way and look at the motions of stars. Stars, of course, feel the pull of gravity, and if there is a massive object there, you could see that in the type of motions these stars have. And indeed, a few years later, we saw the first evidence for mass concentration, and 10 years later, we saw that one star in particular was orbiting on a lifetime of a scientist, once around in 16 years, and approaches the galactic center, compact radio source, Sagittarius A star, to within about 17 light hours. So that's about 4 times the orbital radius of Neptune. So it's that object which, when we discovered it, gave confidence to many, including physicists, that massive black hole exists. But still, to interpret those observations, we assume that GR, general relativity, holds. So back then, in 2002, 2003, we conceived of turning this around. Could we perhaps, the next time this object, this star, would come around in 2018, have equipment and instrumentation such that we could test general relativity and thereby make sure that indeed the theory is correct and that in these very unusual regions can be applied and that these objects are truly black holes. So what you will see today is the first step on a long road the team has done over the last many years and which we hope to continue in the next years as well.
Thank you very much, Reinhard. Our next speaker is Frank Eisenhower, Senior Astronomer at MPE, and he'll tell us about the new results.
Thank you, Richard. Thank you very much. So how do you measure the effects predicted by Einstein? Well, you have to throw a test particle at the black hole. For us, this test particle is the star mentioned by Reinhard. So this is a star which comes very close to the black hole every 16 years, and then it moves at an incredible speed of 3% the speed of light, which is more than 25 million kilometers per hour. And when this star moves very nearby, well then, if Einstein is right, the star changes its appearance. So all the clocks on the star will slow down, and the light, when it travels all its way to Earth, will stretch. The star will become redder from the gravity of the black hole. This is an effect which we call gravitational redshift. So you have to look very close, and this is why we've developed a new instrument. So this is this gravity instrument at the Parallel Observatory, and what you see here in the back are the images from the last 2 years. So we now can make images which are 20 times sharper than what you can do with a single telescope. This is what you've seen. So now with the high accuracy and the sensitivity we have, we see the black hole all the time in the star moving around. Now I have to take you with me as a scientist to actually understand how we measure the effects of relativity. So what you see here on the left is the monitoring of the star over the last 26 years. And on the right side, what you see is a zoom for this year. So what you see here is actually how much better that we can do than 20 years ago when we've seen the star for the first time. Now our accuracy is 100 times better. Actually, despite that the light has to travel 25,000 years from the middle of the Milky Way to us, we can see the star move from night to night. Now the actual measurement of Einstein's effect is a bit more subtle. It's actually a speed measurement in a way. So it's like you should think of a radar speed check with your car. So what we measure is the speed of the star, and this is what you see in this plot. So on the very top right, this peak, this is when the star is very close to the black hole, it moves at a high speed. And now something very strange happens if Einstein is right. When you observe that there is a change in the peak, and, you are lucky, the radar speed check will be lower. The star is not going as fast as it feels itself. And so this is now what you see in that slide. So on that slide, I will shoot two curves. So one is a prediction from what would follow from Newton, and one is a prediction of what would follow Einstein's theory. So the blue line is Newton, and for convenience we make it to 0. This is what we compare to. And red is this prediction from Einstein's theory of general relativity. And so what you see is this effect, what I said. The clocks slow down, you see a redshift, and this is in speed, expressed in speed, 200 kilometers per second, or 700,000 kilometers per hour. So now let's see what we've measured. These are our measurements in 2017, and now while the star was flying by just a few weeks and months ago. And Well, it's your achievement. And what you see is our measurements follow precisely the predictions from Einstein. They are not consistent with what you would have expected from Newton. So if in sports you would say it's a 1-0 for Einstein. Okay, so what does it mean? Actually, really it means a lot, because it was really the first time that we could measure directly and test directly Einstein's theory of general relativity close to a supermassive black hole. And it actually goes beyond that. And it goes all to the root of space-time. So at the time of Einstein, well, he could not think or dream of what we've shown today, but he made Gedanken experiments. And one underlying principle of all of gravity is called the equivalence principle. And what we've shown here de facto demonstrate that the equivalence principle holds in that very strong field around this massive black hole, which then in direct consequence actually leads to stunning results of relativity space-time must be curved. And this is my last slide, which gives you the outlook. Now with our measurements, the door is wide open to black hole physics. So with the gravity instruments and the next telescopes to come, the ELT, we will see many more effects of general relativity in the galactic center black hole. We will see the orbit of the stars to change. We will see light go in circles, and we will even see space-time rotate together with the black hole. Thank you very much.
Thank you very much, Frank. I think the applause speaks for itself. A remarkable achievement. We're now going to hear a little bit more about the technology that allowed this new amazing result to be performed. And we're going to hear from Dr. Françoise Delplanque, who's head of system engineering here at ESO, who's going to tell us a bit about the technology.
Thank you, Richard. Good afternoon. Before going to see those jewel of technologies that allowed those wonderful results, I would first like to introduce you the size that we are talking about, coming a little closer to us. We want to observe a ball of light going around the galactic center. So I try to find an analogy with a football. So let's take the stadium next door and put this stadium on the moon. And then we would like to observe how the football in that stadium is moving during the match. We're observing it from Chile with the VLT, the Very Large Telescope. With those 8-meter diameter telescopes, and without any specific technique in addition, we would see just a blob of light, without any feature. And we could zoom as much as we can, it would still be a blob of light because of the atmospheric turbulence. The atmosphere is scrambling completely the image that we try to obtain. And we cannot get a better resolution than that. If we want to get the nice resolution that those 8-meter telescopes are providing, we need a special technique called adaptive optics that will measure the turbulence generated by the atmosphere and correct for it very quickly so that it irons out all the disturbance, and then we would get an image like that. So that would be the image through an 8-meter telescope placed outside of the atmosphere, or using the adaptive optics technique. So there you can see the central field and the envelope of the stadium. That's about the size. The central field is really very close to the galactic center, where the star S2 is orbiting at its closest. Around are the orbits of the other stars that we see around. But if we want to go even better, we need to get a 100-meter telescope, and then we would get an image like that. And we want to see the trajectory of the ball in that stadium. For that, gravity was designed and is able to measure the trajectory of this luminous ball with an accuracy of 6 centimeters. That means that if ever we get a football match happening on the moon, and we observe the ball is luminous and is observed with gravity, gravity could be used as a video assistant to know if a goal was scored or not. Such is the precision of gravity. So I told you about adaptive optics. Here is what it's looking like. So that's the image of the galactic center without adaptive optics through our 8-meter telescope. We see a lot of stars. They are quite fuzzy. We switch on the adaptive optics, and the lights get concentrated on much smaller surfaces. So that's had different effects. First, you can see more stars that are close by, like you can see in the small insert. In addition, you are concentrating the light, so you get more sensitive, and this sensitivity is a key for gravity to observe the galactic center. And in addition, as you concentrate the light, you see more stars. Many stars appeared on the upper left corner. And concentrating the star on smaller surfaces, you can also better measure the trajectory of the star. You have a better accuracy in the astrometry. And why is Paranal the observatory to do this observation? It's because we have 4 8-meter class telescopes, so 4 very sensitive telescopes, all equipped with adaptive optics thanks to gravity. Those 4 telescopes can, in addition, work together as if they were part of one huge telescope of 130-meter diameter. That's called interferometry. We combine the light of all those telescopes as if they were on the same mount and belonging to the same giant telescope. In addition, the VLT is installed in Paranal, which is an extremely nice site to observe from, with a very good view on the galactic center. And we have, in this observatory, 18 instruments that are maintained by our colleagues in Chile every night to be able to operate, to observe, and we can switch from one instrument to the other very quickly on the same telescope. And that's also key to this observation. Now some pictures, as I promised, about the different technology jewels that we had. NACO was the first infrared camera using adaptive optics that gave those pictures of all the stars moving around the galactic center. Symphony, also using adaptive optics, is the spectrograph that gave the color of the star and how the color of the star is changing when approaching the black hole. Then we have the star of the day, the gravity instrument, using the VLTI, the interferometric facility that makes it a huge telescope of 130 meters. A couple of images. The big things, apart from the telescope, are those delay lines, 120 meters long, and adjusted. Those are optical devices, very accurate optical device, rolling on rails, and those rails are aligned to better than the curvature of the Earth. The Earth is too curved. We had to straighten it up so that everything is aligned perfectly. Because at the end, we want to get all the photons collected by those 4 giant telescopes arriving in the same cubic micrometer, 1 pixel of those detectors, if you want. And those detectors, we had to develop them for gravity as well, in collaboration with the industry, to have very sensitive low noise detector. So gravity obliged us, ESO, to push the infrastructure that we had, the interferometer, to its physical limits. We had to develop those new detectors. We had to prevent those huge telescopes from vibrating. They are vibrating at a fraction of a micrometer, so a very, very tiny amount. And all that was needed. We had to install 4 adaptive optic systems at the focus of the telescope. All that so that gravity can reach its accuracy and sensitivity. And gravity itself had a lot of further challenges that will be presented in the next talk. Thank you.
Thank you very much, Françoise. We're now going to hear more about the gravity instrument itself, and the speaker is going to be Dr. Karine Perrault from IPAG in Grenoble.
Thank you. As explained previously, if we want to be able to measure the motion of S2 with such an exquisite accuracy, we need to go far beyond the capabilities of adaptive optics and combine the light of the 4 8-meter telescope together to do what we call interferometry. So the photon collected by each telescope travels in tunnels of several tens of meters and feeds the gravity cryostat that hosts the Wool interferometric instrument. Cooling down the instrument down to minus 200 degrees allow to improve its sensitivity. To reach the high accuracy, the beams are controlled all over the instrument, first at the telescope level with the adaptive optic systems, and then at the entrance of gravity, where some photons are used to check the beam and the image quality. What is really important is while interferometry has been used for several decades to do the science of gravity, we had to push drastically both the accuracy and the sensitivity. And these efforts allow us to reach a new regime and first to give for the first time access to scientific studies of faint objects by infrared interferometry. The light coming from the galactic center is focused in single-mode fibers that clean the beam, and half of the fibers feed a dedicated system that allows to stabilize the signals with a monitoring and a correction every millisecond. And this stabilization allows us to integrate the photons from the galactic center over minute-long integrations, and then to detect the faint signals. At the end, the photons coming from the vicinity of the massive black hole are injected in an integrated optic chips in which the beams coming from the four telescopes are mixed together and where interference fringes are produced. And we do not observe images, but this succession of bright and dark zones that are characteristic of the source and from which we can reconstruct images or deduce accurate relative position on sky.
Thank you very much, Karine. It's a remarkable instrument to see in so much detail. Our final speaker is Dr. Odell Straub from the Paris Observatory, who will summarize the significance of the result for gravity theory and look a little into the future. So over to you.
Thank you very much. So we went to Chile several times, and we used these beautiful and complex instruments to measure a relativistic effect in the center of our galaxy. Why is this important now? Why did we do this at all? So you see, gravity is a fundamental property of the universe. Understanding gravity here on Earth, in the solar system, in the Milky Way, outside of the Milky Way, this is the key to understanding the universe. And this is what we really want to do, right? We want to know in what kind of a universe are we living. And to do that, we were looking at the galactic center. The galactic center was our laboratory to test gravity. And for the first time, we tested gravity in a galactic center, in general, with a massive black hole and a star that goes around it. So this is the big thing, really. And what we saw is, yes, the black hole, it behaves like Einstein's black hole. It cannot be described, what we measured, it cannot be described by Newton anymore. So, what did Newton say? Newton realized that gravity is intrinsically connected to mass. In his Principia, he wrote, mass gives a body heaviness, and in Latin that means gravitas, gravity. So the idea Newton has, which was later called the universal law of gravity, is that gravity is a force that acts between two masses. It's an instantaneous force, and it is what makes objects fall, here in the picture, an apple, and it is also what keeps planets on their orbits around the sun. This is a universal law. It works very well everywhere, except there is one planet that doesn't quite play by the rules of Newton, and this is the innermost planet, Mercury. The innermost planet goes so close to the sun that it feels, well, I I don't know whether Mercury has feelings, but it feels not only Newton's gravity, it feels something more. It feels something that can only be described by Einstein. And that is an additional kick, which kicks it into a kind of a Rosetta orbit combined with Newton. So what did Einstein say about gravity? To Einstein, gravity is not only connected to mass. To Einstein, gravity is connected to mass and to space and to time. Everything is connected, really. So in Einstein's theory, you have space-time. This is time and space combined to a fabric. And if you put a mass inside it, this space-time, it has to curve. And this is what the blue picture there shows. Curved space-time. And there is a very beautiful quote by John Wheeler that says, mass tells space-time how to curve. And space-time, in return, tells matter how to move. And this is basically the essence of Einstein's theory. And the cool thing really is that space-time is not only telling matter how to move, it's also telling light how to move. And this comes with very interesting effects. So the first picture on the top right, you see this is simply Mercury's orbit, which is being kicked by the joint Newton and Einstein gravity into a Rosetta. But the second picture is the solar eclipse in 1919, where light bending was observed. So light has to bend according to the space-time fabric, and this can be observed. And the third bottom picture is even the coolest, because that's what we are doing, right? This is called the gravitational redshift. And I have now a small present for you. I drew you a cartoon to show you how this works. So this is it. What you see is the galactic center simplified. The black dot is the black hole, very far away in the galactic center, and the star is S2. The star goes around the black hole. The star shines, it emits light, and light is composed out of photons, and these are these little fellows you see there. So the light has to travel from the deepest depths of the galactic center all the way to us on Earth. And every time when the star is very close to the black hole, light feels not only the star, it feels also the black hole. And this has an effect on the light. The light is getting, it has to fight against the joint gravity of the star and the black hole. And the light is getting a bit tired. And this is what this cartoon is supposed to show. It starts out very energetically blue. It has a very short wavelength. And as it has to climb away from the star and the black hole, its wavelength stretches. If it would be a normal particle, it would probably lose energy by getting slower, but light can't get slower. It always travels at the speed of light. So it has to keep the speed. The only way it can lose energy is by stretching its wavelength and becoming redder and redder, and this is what we saw. We saw the reddening of light. And now that we have this beautiful laboratory in our own galactic center, we can do all kinds of new things. So there are things we plan to do in the very near future, and that is, well, the first picture now is not Mercury anymore, it's supposed to be S2, because S2, the star, it is also supposed to move in a kind of a Rosetta way, and we want to see this. And in the next few years, we hope to do that. The second picture is the black hole spin. What we also can do is, in the near future, measuring the spin of the black hole in the center and how it drags the whole space-time around it. This will result in further funny effects. And also what you surely have heard about is the black hole silhouette, which is the black hole silhouetted against the gas that surrounds it, its immediate environment. It creates some kind of a crescent, luminous crescent around it. And last but not least, what we hope to see also in the galactic center is gravitational waves of stuff that falls into the black hole. So these are the prospects. Thank you very much.
Thank you very much, Odell, and thanks to all our speakers today. I'll leave that picture up. So the floor is now open for questions from people here. To start with, we have some.
Thank you. Thank you very much. Dorothy Smith-Gardner of the Universe blog. My question is, to what degree would you consider Einstein's theory as proven with your result?
Maybe you could take that one.
I think it's a step on the road. Okay, there are many steps to take, but this one was passed with pretty good colors and flying colors. But there are more to do, and in fact, that's the steps which Odell showed you. And in fact, even if we have gravitational waves, which in many ways comes closest to such black holes, there is still more work to do to really come as close as you can to the event horizon where you might expect strong deviations from gravity, from Einstein's theory.
Anyone else in the room? Questions? Press the button.
Yeah. How long do you think you have to observe now the orbit of S2 with gravity to see the perihelion precession? Do you have to wait another 16 years, or will you get it faster?
Well, we think we will see it next year.
The young man has a lot of courage.
He did use the word think, though. Didn't he? Yes. Okay. Okay. Any other questions from people here? Okay. We have a few questions online. Let me see. Yes. A blogger in the UK is asking whether there are stars orbiting close to the black hole. Are any of them going to be eaten by the black hole? And if so, when and what would happen? Maybe one of you would take that.
Well, this is at the moment rather unlikely to happen. So just as the Earth is orbiting the Sun and the Earth is not falling into the Sun, also these stars don't fall into the black hole. Only in very rare cases, when a star is really on a radial orbit, it might hit the black hole. But these stars are very rare. The ones we observe for now are all well behaved and will remain around the black hole.
Okay, thank you. So no fireworks in the near future. Right. Okay.
Richard?
Right. Sorry? Yes. Press the button.
Yeah. Well, I think it has not been observed that a normal star hits a black hole and it's disappearing immediately. But there have been, in X-ray astronomy, there have been events coming from centers of galaxies, not from our own galaxy, from other galaxies, which show an enormous peak and then a decline of the intensity over several years. And the only interpretation of that is that a normal star gets very close to the black hole and it is torn apart by tidal forces. It's producing accretion disk, and this accretion disk is gradually swallowed by the black hole.
Okay. Thank you very much. So it does happen, but not often. Let me see. Okay. I have a question from Matteo Marini from La Repubblica in Italy. And he asked, what observations are still lacking for general relativity to be proven? What are you going to observe next? So maybe that can go to... Yeah.
There are never enough observations to prove a theory 100%. There is no such theory, really. What we actually hope is that perhaps at some point we will see something in the galactic center that we can't explain with Einstein's theory. That would be really, really, really exciting, because then we can go back to the drawing board and we can come up with a new theory that is better in describing the universe. So I hope there will be observations that can't be described.
Thank you very much. I have a question now from Camille Carlisle, who writes for Sky and Telescope in the US. And she says, let me get this right, S2 has only gone through one of the 2 expected radial velocity turning points for this year. What will observing that second turn this September tell you about the gravitational redshift?
Now, the curve is actually not centered on these turning points. So the turning points which you saw in Frank Eisenhower's presentation actually are Newton. You couldn't, on that graph, see Einstein. Einstein is embedded in there as a few percent effect on top of the general rotation of the star. So these turning points are created because the star is taking the turn around the black hole. And so if you subtract that, then you see a curve which is centered sort of more or less in the middle of these 2 turning points and falling off smoothly on either side. So I would expect that from now on until the end of the year, when we can't observe anymore, the effect of general relativity will, on that one, on the gravitational redshift, will go slowly down. At the same time, however, the other effect, which is the precession due to the orbit, will come into play more and more.
Okay, thank you. That leads very nicely into the next question from someone called Rob Banfield, who asks how much precession of S2's orbit is to be expected in degrees per orbit.
So the precession, if you compare it to the Mercury precession, which I think is 43 arc seconds per century, is rather large. It's on the order of 0.2 degrees per revolution for S2, so 0.2 degrees in 16 years. However, the orbit is only as big on Sky as a football stadium on the moon would appear, as we've just heard, and that makes it a very small number then to measure in the end. And that is why we haven't seen it yet, but
Okay, thank you very much. I think that's about it for the online question. Any more questions in the room? Okay. Well, in that case, I think that's the end of the press conference. And I'd like to thank everyone for joining us, both online and here. There's a lot of people in the room. And we have some light refreshments outside, which people are welcome to partake of. And I'm afraid people online will have to find their own refreshments. But thank you, thanks again to everyone. Reinhard would like to make one final comment.
As an old man, I can say this is a proud moment for the organizations involved and the young people who really have spent so much time on this very complex experiment, which certainly, from my perspective, was the most complicated thing we could think of. And in fact, one a priori could have said it can't never work, and it did work. And Frank, I mean, you really, with your team, you are a genius. You have done so much work. And I know that half of our co-eyes are in the room, so let me bow to you and thank you very much for participating in this, making nights, days, working on the mountain. Whereas Andreas Kaufer with his team, wonderful, wonderful cooperation. And to you, Director General, thank you very much.